Hello everybody, new year has started and we will go right into our next topic, which is about eigenvalue problems. Of course, we restrict ourselves to quadratic matrices to this end. This is the exercise sheet number 3.5, by the way. The question is almost always the same. If you look at such a matrix, this is a very simple example to start with, 2 times 2 matrix of this sort. It's interesting by itself because you can make a short analysis of this kind of matrix, and you will find out that it, geometrically speaking, it performs a very special operation if you apply it to the vectors, to the 2D vector space. And so it would be rather easy to predict what its eigenvalues and eigenvectors are. I suppose that you're all familiar with this kind of question, which we always ask, namely, which are those special vectors whose image, by applying the matrix, points in exactly the same direction as the pre-image. That's, you could say, the definition of an eigenvector. Okay, so an eigenvector is such a vector which is rather special, one must say. It's not the regular situation. It is a vector which does not change direction if you apply the matrix to it. So firstly, this is a striking aspect, because generally speaking, most vectors do change as well their direction as their absolute value if you apply a matrix to them. Okay, so how to find these special vectors called eigenvectors? Interestingly, I must add that exactly the scaling factor by which such an eigenvector is scaled, if you apply the matrix, is then called its eigenvalue. Now, it turns out that it's always necessary, or you could say, yes, it's almost impossible to determine or to calculate an eigenvector before you have determined the corresponding eigenvalue. So that's just part of this solution method. You know it all, you know all of this. And so I will start the following way. I will tell you, without a proof now, that this kind of matrix turns out to be a so-called shear matrix. You've probably heard of this. What is a shearing operation? In this case, it's a horizontal shear which takes place. And you can look at this picture. So I think this explains it most easily. If you ask yourself, what would, look at this square. Just imagine that we have a two-dimensional vector space, so it's the plane, and the whole plane would be the vector space, and the origin should be here, where these orange and the red arrow touch each other. Okay, so I have, you could say this is the base, one valid basis of this vector space. The orange one to the right and the red one upwards. So if we look at this square and we ask what would, in geometrical perspective, what would the result of a shear operation be? And this is what happens. Okay, the whole, this is, I draw this square just for you to visualize what happens. Okay, so it's not really mathematically active. It's just for visualization. So you would, it's hard to say for me now in English, you would transform it in the way that it looks like this afterwards. Okay, so you see that the baseline of this square has been, well, shifted to the left, while the upper side here has been shifted to the right. And also the other two sides, well, they result in under a certain angle here, as you see. So that's a parallelogram which results. Now, simply speaking, the main effect of such a shear operation is that you have in this horizontal direction, you have a movement. It's like, now let's look at the vectors. The red vector, its arrow here, you know, the endpoint, it's shifted to the right, while the orange one is not changed at all, because it's lying on the horizontal baseline. So that's simply speaking the effect, and you can describe this whole geometric effect by a so-called shear angle, which I put in here, alpha. And it's obvious that in this example, this shear angle is exactly 45 degrees. Mathematically speaking, it's pi4, you know, okay? The half of a right angle. So why do I know this? Because it turns out that this is the general form of such a horizontal shear matrix. You can, by the way, you can test it by just applying it to, for example, to a unit vector of this type and one of this type, and then you will see that exactly what I showed you here will happen. So this is, we don't have the time now to check it, you just believe me. And so in the end, it always looks like this. It's like, you could say it's a unity matrix, 1, 0, 0, 1, modified in a way that this element is replaced. So this would originally be a 0 for the identity map, you know, and this is replaced by a constant. In this case, it's a positive constant. Exactly speaking, it's equal to 1, but it could also be any other value unequal to 0. So if it's a positive value, and if, in this special case, if it's 1, generally speaking, you can identify the shear angle by the fact that this constant is the tangent of this shear angle. These are facts, okay? You can take it for granted. So in this case, we have tangent of alpha equals 1, and we all know that the special angle of pi4 is the one whose tangent is equal to 1. You know what this means, or where this comes from? It's because it corresponds to a isosceles and rectangular triangle, where both sides, the side opposite and the side adjacent to this angle, are equal, have the same length. Okay, so that's not really a big surprise, but now we can predict sort of that this is what will happen. And if you look at this again, you would predict that the only kind of eigenvector we would expect is one of the orange sort. Better speaking, it must be a horizontal vector, because obviously this is not changed at all if you apply the matrix. You can also test it. It's a vector 1, 0. Okay, if I apply this matrix to the vector 1, 0, I have first row times column. You remember the Ertag principle? So it's 1 times 1 plus c times 0, so it remains 1. And then the second row times this column, 0, 1 multiplied with 1, 0 results to 0. So the input vector 1, 0 will be unchanged by applying the matrix. It will the image vector will be 1, 0 again. So that's no surprise. Also, but yes, if this is the case, then looking at this little sketch here, we would expect no more eigenvectors to exist, because the red one wouldn't work. It changes direction, as you see. And since if there were another, it would have to be linearly independent, and there's no way to find any vector except for these horizontal ones, which do not change direction. So it's quite clear we will have one eigenvalue, which is 1, because the vector remains unchanged, and exactly this horizontal direction as the eigenspace of this eigenvalue. So that's like a prediction, but then let's look at the official method to solve this, okay? So that's the following. First, you remember from the lecture, I hope. First, what we do is we subtract sort of a unity, I call it E, but that's probably we should use I, that was our usual symbol. E is for the German Einheitsmatrix. Okay, so this way. So what we do is we take the identity matrix and scale it up by an unknown factor of lambda, which will be the eigenvalue in the end. Okay, so you remember this. So this is the trick. And then we take the determinant of this construction, which is matrix A minus lambda, unknown, times unity matrix. And what happens is always the same. The effect of this is that on the diagonal, exactly on every diagonal element, lambda, unknown, must be subtracted. And all the other elements of the matrix remain unchanged, of course. This is it. Okay, so we have 1 minus lambda here, 1 minus lambda here, and this remains 1, 0. And then we take the determinant. Of course, this is quite easy now with the 2 times 2 matrix. As always, we have the diagonal product, which is 1 minus lambda in parentheses now, times itself, so to the second, to the power of 2. So this parenthesis squared, and minus the second diagonal product, which is 0, so that's all. And now that's important, we set this determinant equal to 0. You know why we do this? It's important to do because only if this matrix is singular, we will find a system of linear equations, in this case 2 of them, okay, which has a non-trivial solution. And from the proof of all of this, it turns out that only a non-trivial solution to the corresponding SLE will give you a valid eigenvector. Okay, so first of all, find all the values of lambda which fulfill this equation. And now in this case, it's quite easy. We have 0 here, so we can take the square root, of course, with case distinction plus or minus, but it does not really matter. In the end, we will have 1 minus lambda equals 0, and then finally lambda equals 1. I call this result, this eigenvalue, the solution number 1 and 2, just to denote that this is a double solution of this equation. Okay, of course, this is an algebraic equation of 2nd grade, and it should have 2 solutions. In this case, we have 1 double solution, so that's fine. Now, the other point is, which you know, is I'm just asking myself, have we done this before? I think we have talked about the multiplicity, geometrical versus algebraic multiplicity. But probably this was, yeah, at least I don't remember to have solved this with you. No, we haven't. Okay, so it's fine. Anyway, this is the so-called algebraic multiplicity of this solution, okay, of this eigenvalue, then solution to this characteristic equation, as we call it. And of course, if that's all we find, if you add together the multiplicities of all solutions of this equation, it must always be the grade of this equation. And so this means it must be the dimension of the matrix. That's a fact by the fundamental theorem of algebra, at least if we allow for complex solutions. And this is what we do usually, okay? But now the interesting point is that the sum of the geometric multiplicities of all the eigenspaces which we find corresponding to the found eigenvalues must not always be the same. It can be lower than the dimension of the matrix. So actually, in this case, this is what happens. In this example, we will find only a so-called eigenline, which corresponds to one direction for eigenvectors to this eigenvalue, although this is a double solution of the equation. So this is not a surprise. It can happen. Sometimes it happens, sometimes it doesn't. Of course, there are certain attributes of the matrix which decide whether it happens yes or no, but it's not so important at the moment. Just a second. So now, after we have found a valid eigenvalue, like the 1 in this case, Then the next step is to insert it into this original approach. But don't forget now to leave away the determinant operator. Because now we know that if we insert 1 for lambda, we have a matrix altogether whose determinant equals 0, so it's singular, and we will expect to find a non-trivial solution. So the solution will be a manifold. It will not be a unique solution. That's what we want in this case. Okay. So I will do this. I use parentheses instead of these, these determinant bars, and I write a minus this value to insert here 1 times, now again unity matrix, of course, and then times, so this applied to a location vector x should be equal to the 0 vector, because we are looking at the homogeneous SLE always in this case. So you know where this comes from when you look back or think back, remember what you saw in the lecture. So anyway, now inserting, look here, I have 1 minus 1 is 0, also here 0. So everything that remains is 0, 1, 0, 0. And it's no surprise at all that we have a 0 row here. We expect to get a 0 row, not necessarily all at once, but latest if we would apply the Gaussian or the Gauss-Jordan elimination method, at some point we would have to get a 0 row, otherwise there would not be a non-trivial solution. So that's always the case. It's also a good test for you to see whether you found the correct eigenvalues, because only if by insertion of each of the found eigenvalues in this matrix construct here, then it must be the case that at least 1 0 row comes along. Okay, so anyway, what do? We can cross this out because it's just a missing equation. Also, because it's a homogeneous SLE, there's never a contradiction. So it's just like saying 0 equals 0. We just look at this row, and everything this row contains is, we can just read it out. Okay, we can fill in our unknowns here, or the components of our location vector. So it means 0 times x1 plus 1 times x2 equals 0. That's just the explicit version of this row. Okay, and now you just bring this in a in a little other form. Okay, now in this case it's done because the first component just disappears, 0 times x1, it goes away. It's everything that remains is x2 equals 0, and that's all. Because if this is the result of, if this is the general solution of this SLE, it means that every vector which fulfills that its second component equals 0 is an eigenvector to this eigenvalue. So this was a simple example just for you to get into the topic. And so in the end, we can say eigenvector, I say lambda, this index is then the value of the eigenvalue, the actual eigenvalue. I could also say x vector 1, but then the 1 would not denote any component. It would denote the value of the eigenvalue, sorry. Anyway, the important point is that this vector 1, 0, which fulfills this equation, is already a valid eigenvector then for this eigenvalue 1. But also, so this is important to know, any other vector which points in the same direction. In this case, it's a 1D eigenspace. We can also say it's an eigenline, yeah? And so, exactly speaking, this is the set of all vectors which fulfill this result, this equation, and which are eigenvectors for our eigenvalue 1. So it's all vectors u0, where u is element of R, real numbers, but excluding 0. This is important. You must always remember, mathematically, if we would allow the 0 here, we would have the 0 vector as an eigenvector. Mathematically, it's a difficult question, actually, because the 0 vector, you could say it always works as eigenvector. This is because if you apply any matrix to the zero vector, it stays the zero vector. So you could say it's always an eigenvector. But there are two problems. First problem is the zero vector is just not, let's say it's not interesting. It doesn't help you in any application, for example. But the more important problem is you can, by principle, you can never define a corresponding eigenvalue. Because if I would try to scale the zero vector by any factor, it would always stay the zero vector. So if I count it as an eigenvector, I would have to say that whatever you want, any number, any complex number even, would be an eigenvalue for this zero eigenvector. So the consequence is just to exclude it. Okay, so any vector on this horizontal baseline of the vector space, as you have seen in the sketch above, except for the zero vector, is now a valid eigenvector to this eigenvalue 1.